Hi, welcome back. In this video, we're gonna apply the contact stress equations to calculate the maximum contact pressure, the width of the contact, the maximum shear stress, and the depth below the surface where the shear stress is maximum. This is gonna be for the case for where we have two mating steel spur gears. So as you know from the contact stresses equations, usually we have two sets. One is for when we have two spheres in contact, and the other one for when we have two cylinders in contact. So the first question that you want to ask yourself is, do I want to model this as two spheres or as two cylinders? So to better answer that question, we're going to look at this figure over here where we realize that because the gears have this face width over here, and it's going to be making contact somewhere over here. Yes, they give us a radius, right? But really that contact is going to have a length associated with it. In this case, it's going to be the face width of the spur gear. So what that means for us is that we're going to go ahead and use the equation for the cylinder contact. So again, because we're calculating the contact pressure and B over here, which is half the face width, and both of these equations, again, depend on the force between the two cylinders, the radius of the two cylinders, the length of the cylinder, which in this case is the face width of the spur gear, and the parameter delta. And these are going to show up for the two equations. I always suggest let's go ahead and solve for the delta first. Right? So we have, in this case, steel. So steel is going to have a Poisson's ratio of 0.3 and an elastic modulus of 207 gigapascals. Now, when I do this, I like to work with units of megapascals, so I'll write it as 207,000 megapascals. Right? So with the Poisson's ratio and the elastic modulus of steel, and because in this case both the gears are made of steel, we can go ahead and substitute the values in this equation. So this is going to take the form of 1 minus 0.3 squared divided by 207,000 plus 1 minus 0.3 squared divided by 207,000. And so the values that I get for delta is 8.792 times 10 to the minus 6. Again, on the top we got Poisson's ratio, which is unitless. On the bottom we have the elastic modulus, which I have in units of megapascal. So this has units of 1 by megapascal. So contact pressure is going to be 0.564 times the force, which is 250 newtons, times 1 by R1, 1 by R2. So here I went ahead and labeled this blue gear as 1 and the purple one as 2. The order doesn't really matter much. So 1 by, and notice the radius is given on the figure as 10 millimeters. Plus 1 by R2, or 1 by 15 millimeters. So this is what we have on the top. On the bottom, we're going to have the length over here. The length over here. So the length would be the length of the cylinders, which in this case would be the face width of the spur gears. So I don't have one written down over here, but let's just assume that the face width for this gear was an inch or 25 millimeters. So we'll put 25 millimeters as the length, and then we have our value over here of delta. So delta we calculated to be 8.7923 times 10 to the minus 6. And so now let's take a look at the units. On top we have Newton per millimeter. Over here I have millimeter. And the delta value has units of 1 by megapascals. So remember, a megapascal is the same thing as a Newton per millimeter squared. So this is the same thing as saying millimeter squared by Newton, right? So this is the same thing as saying millimeter squared by Newton. And then remember, we're going to take the square root of all this thing. So let's see what's going to happen. We have Newton up on top, and we have a Newton at the denominator, which is going to bring it up on top. So we're going to have units of Newton squared. So when we take the square root of that, it's going to give us just a Newton. So we're going to have Newton up on top. Now let's see what we have in the denominator. So in the denominator, we have millimeter squared times a millimeter, that's millimeters cubed. And remember, we have this millimeter unit up on top, but it's in the denominator. So we multiply that again. So we have 2, 3, 4. So at the bottom is going to have millimeters to the fourth. However, we're getting the square root of that. So it's going to give us back just the millimeters squared, right? So whatever we type in, all these numbers in the calculator, the number that we get is going to be in newtons per millimeter squared, which is going to be the same thing as a megapascal. So I'm going to go ahead and type the values over here. 0.564 times the square root of this big old fraction, which is 250 times 1 by 10 plus 1 by 15. All of that divided by 25 times 8.7923 times 10 to the 6. Negative 6, I'm sorry, times 10 to the negative 6. So if I did not make any fat finger mistake on my calculator, I'm getting a value of 245.6. Again, what comes out of here is Newton per millimeter squared, but that's the same thing as a megapascal. So essentially, this is 245.6 megapascals. I'm going to go ahead and write that number down over here. Contact pressure is 245.6 megapascals. So next what we'll do is we're going to calculate that B. So remember when we're finding B, when we have two cylinders, so I'm going to exaggerate this drawing. So let's say I have a cylinder and it's in contact with another cylinder, so it's going to be kind of flat. I'm exaggerating. And then I have another cylinder in contact. Right? This is the contact width. However, this B parameter is from the center to the side. So B is here. So said otherwise, the width of contact is going to be twice the B. So let's go ahead and calculate what the B value is. So the B value is 1.13 times the square root of the force, which is 250 newtons. Delta, which is 8.7923 times 10 to the minus 6. Remember, this has units of inverse megapascals or millimeters squared by Newton. And then this is going to get divided by the length. Again, the length is the length of the cylinder, which is going to be the face width of the spur gear, which we said we were going to use 25. So $25 millimeters. And then it gets multiplied by 1 divided by radius 1 plus 1 divided by radius 2. So 1 divided by radius 1, which we said was going to be 10 millimeters, plus 1 divided by radius 2, which is 15 millimeters. And then we take the square root of this whole thing. So let's check at the units real quick. We have millimeters, but it's going to multiply by this quantity, which has millimeters in the bottom. So these guys are going to cancel with these. So there's unitless in the bottom. In the top, you have this Newton, which will cancel with this one, and we're left with millimeters squared. However, we're taking the square root. So when we type all these numbers in the calculator, the number that we get is going to have units of millimeters. So 1.13 times the square root of the fraction, where I have 250 times 8.7923 times 10 to the minus 6 on top. On the bottom, I have 25 times 1 over 10 plus 1 over 15. And if I didn't mess up the calculations here, I'm getting a value of 0.02. I'm going to round here to 126 millimeters. So remember, this is just half the width. So the width of the contact is just going to be 2 times B. So answer times 2, and we get that the width is 0.0519 millimeters, right? Or if we move the decimal 1, 2, 3, around 51 microns. So next, let's calculate the maximum shear stress. This is an easy one. We know for the case where when we have 2 cylinders in contact, the tau max is simply going to be 0.3 times the contact pressure. So the contact pressure was 245.6. If we multiply times 0.3, we're going to get a tau max of 73.7 megapascals. So that's the answer for the maximum shear stress. Next, we need to answer the question of at what depth does this value occur? And if we look at the plot for the stress distribution as a function of depth below the surface, we see that the maximum shear stress is going to occur roughly between 0.8 to 1B in millimeters depth below the surface. So I think a better approximation would be that this occurs at 0.8 B. So if our width, not the width, but the value B over here, 0.26, if we multiply times 0.8, so take 0.026 times 0.8, we're going to get roughly 0.021 millimeters. So that means that 0.21 millimeters below the surface, so we can go this direction or this one over here, that's where the maximum shear stress is going to act.